All right, welcome. So in this section, we're going to talk about tangent planes and linear approximation. It's very similar to what you do in Calc 1 when you talk about tangent lines. So let's just sort of review that. Okay, so if you're given, let's say y equals f of x, the equation of the tangent line at x equals x0 is y equals f prime of x0 times x minus x0 plus f of x0. Okay, so if you want to draw a picture of that, let's do it a little neater there. Okay, so you have x0 there. This point here is x0 f of x0 because this is y equals f of x. Okay, and your tangent line is this thing, right? It has a slope given by the derivative at x0, and it goes through the point x0 f of x0. Okay, so we're going to do the same thing, except for now we're going to do it in 3 dimensions. So let me give you sort of it's really, there's nothing to it as far as like if you look at it that perspective. The tangent plane to z equals f of xy at x0, y0, okay, is given by z equals, now we're going to have the partial derivatives here. So we're going to take f sub x, x0, y0, x minus x0, plus f sub y, x0, y0, y minus y0, plus f of x0, y0. Okay, so if you want to look at this sort of in a graphical way, if you're more of a graphical learner, say we have our function. Now our function, remember, is z equals some function of x and y. I'm not so good at drawing this, as you guys already know, but I'll do my best. So let's say this is some point x0, y0 here. And our curve does some crazy stuff. Ooh, right there. This is where we care about it. Okay. And so what we're going to do is we're really taking the derivatives in both sort of the x direction and the y direction. So in the x direction, that means as we go in this direction, we're going to have sort of a, like a curve there. Okay. As we go in the y direction, as we go in this direction, we're going to have sort of a vector here. Okay, and remember, a plane is defined by any two vectors or any two lines, and you also get the normal vector, which is perpendicular to it. So this is our normal vector. Okay, so we're going to go ahead. We're here. We may as well sort of do this. I'll show you guys what I mean here. So this vector here is actually, instead of fx x0, y0, well, let me roll back here. When we were doing one dimension, when we were doing slopes just slopes. Remember, I sort of harped on this a little bit. I said M sort of has this representation as a vector of 1M, right? Which means as you move 1 to the right, you go up by M. Same thing here in 3D, okay? fx0, fx of x0, y0 is going to have a vector representation. Be very careful with it, though. Its vector representation is 1, 0, fx. Okay, how is that so? What I'm saying is, as we move 1 in the x direction, z is going to increase by this amount. Okay, or decrease, doesn't matter. That's how z is going to change. Okay, likewise, fy of x0, y0, how do you think that changes? How do you think we're going to represent that as a vector? Okay, it's actually going to be 0, 1 f sub y. Okay, what's happening there? As you move in the y direction, that's this 1, you're going to go up or down by f sub y. Okay, so what's our normal vector? Our normal vector is going to be, as usual when we're doing cross products, the determinant of I, j, k, 1, 0, f sub x, 0, 1, f sub y, and this comes out to be, so let's just take the i's, 0 is going to be, I won't do it for you, or I will do it for you, but I won't, you know what I mean. I've already done it. It's going to be negative f sub x, negative f sub y, y. So that is our normal vector. Okay, so let's take a look at the equation of a plane. Now remember, running out of space, we'll go to the next page. Recall. Okay, equation of a plane through the point x0, y0, z0 with normal vector n equals a, b, c, okay, is a times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0, right? That comes from that. You take the normal vector and dot it with a vector that's supposed to be in your plane. Okay, so we're going to do that with this. So what's our normal vector? Well, here our normal vector is this thing. Okay, our point is x0, y0, z0 is f of x0, y0. Okay, so now let's go ahead and do this dot product. So we take negative fx times x minus x0 minus f sub y times y minus y0 plus 1 times z minus f of x0, y0. That should all equal 0. So let's solve this to get z on one side by itself. If we do that, I'm basically going to leave z on this side and move everything else over to the other side. So we're going to get z equals fx, x minus x0. Remember, it becomes positive because it moved to the other side. Plus f sub y, y minus y0, plus f of x0, y0. And if you look, that's exactly what we got when we just extended the one-dimensional version. Okay, so it's just two ways to understand it, but this is, I like this way better because it's sort of, it comes out of the geometry. But I also like this way better because it's just an extension of the one-dimensional version. Okay? All right, we'll come back and do some problems in the next video. If I can ever stop this.